Thank you for virtually attending this talk. So today I'll be discussing recent exciting results on robust algorithms for the TSP and Steiner tree problems. This is based on joint work with Bruce Maggs and Debmalya Panigrahi. So most people watching probably know the definitions of these problems very well, but let's go ahead and review them. So in both the TSP and Steiner tree problems, we're given a weighted graph G, and in the TSP problem, given G, we want to find the shortest tour, and a tour is just any cycle visiting all the vertices. So in this example graph on the right, I've highlighted the shortest tour using the bold edges. And in the Steiner tree problem, in addition to the graph G, we're given a subset of the vertices T, and our goal is to find the lowest weight tree that connects all the vertices in T. So in this example, I've highlighted T as the golden vertices, and again, the bold edges give an example of a minimum Steiner tree. So both problems are NP hard. However, the result of approximation algorithms is very, very good. For the TSP problem, there is a 1.5 approximation algorithm, and for the Steiner tree problem, there is a roughly 1.4 approximation algorithm. So both problems, of course, have a variety of applications, some of which I've listed here. However, the problem with translating the results in theory for these problems, which are very, very strong, to strong practical results, is that in practice, many of these applications come with a lot of uncertainty. For example, suppose I want to use a TSP algorithm to route a vehicle in practice. One thing I have to contend with is the fact that travel times between 2 points may be very uncertain due to factors like unexpected construction or traffic jams. So this poses an algorithmic challenge because if we'd like to use classic approximation results, these results assume perfect knowledge, and we don't have perfect knowledge in practice, so they may lead to very poor results. For example, let's say I have this example graph from before, and I'm trying to solve the Steiner tree problem, and I choose the solution in the bold edges. However, maybe when I deploy the solution in practice, the cost of these edges actually changes slightly for every edge, and now what was once an optimal Steiner tree is actually a very poor Steiner tree. So this poses a question of, on the theory side, how should we handle these uncertain inputs? So let's discuss the approaches to handling uncertainty that are common in the theory community and see what their upsides and downsides are. So one approach, which we discussed on the previous slide, is to just assume that we have perfect knowledge of what the edge lengths are going to be in practice. So the upside of this is that we have very good algorithms. The downside is that this assumption is probably going to be poor in practice, and this may lead our very strong theoretical results to be very weak practical results. A second approach is to assume we have slightly weaker knowledge and assume a distribution on each edge length rather than a fixed perfectly known edge length. So an upside here is that this is probably more robust in practice. However, there are some downsides. One is it's unclear if robust algorithms exist. It's trivial to, for example, get algorithms that have good expected cost, but it's unclear if we can get algorithms with good expected cost and low variance. In addition, estimating a distribution on edge length in practice may be very costly, and if our entire point of running the algorithms is to reduce the cost of the final solution, this may be counterproductive. So the approach we'll discuss in this talk is the most robust one, which is rather than predict a perfect edge length or a distribution, we'll just predict an upper and lower bound on each edge length. So the main upside of this is that the results are very robust in practice because we have some uncertainty baked into the inputs. In addition, predicting the upper and lower bound on edge length is probably going to be much cheaper than trying to predict an entire distribution, and these assumptions or these predictions may still be very reasonable in practice. So the main downside and the challenge that we try to address in this talk is it's unclear if good algorithms exist in this model. So let's formalize the model that we'll be using through this talk. So I'll call this model a regret minimization model. And in this model, when we get the graph, we don't have specific edge lengths. Instead, we have a prediction for a range of edge lengths. So for edge E, I'll denote the range of possible edge lengths as LE to UE. So let's say we choose a solution alg. Here I've highlighted alg in the bold edges. And now how do we evaluate the solution? Well, we want the solution to be robust to every possible setting of edge lengths that satisfies these ranges. So what we could do is we could imagine that nature or an adversary reveals true edge lengths D that satisfy that each edge length is between LE and UE. Now, if nature wants to make our solution look as bad as possible, it'll maximize the length of all edges in our solution and minimize the length of all edges outside our solution. Now, given these revealed edge lengths, we could say, what cost did we have to pay for not having total certainty about the edge lengths? So in particular, let's consider what the optimal solution is, and let's define our regret to be the difference between the cost of alg, our solution from before knowing the true edge lengths, and opt, the best solution after we see the true edge lengths. So here our solution costs 14 and opt costs 5, so the regret of this solution is 9. So now our goal is to find a solution with minimum regret. So here's another Steiner tree solution. And again, if we repeat the same process, so the adversary sets all the edge lengths in our solution to be as large as possible, all the edge lengths outside the solution to be as small as possible, and then we choose opt given these edge lengths. We can see here that, for example, this solution has regret 4. And let's do this one more time. So here's yet another solution. And again, if we repeat the same process, we'll see that the regret of this solution is 2. And in fact, this solution is the solution that minimizes the regret. So we'll call this the minimum regret solution, and we'll denote its regret by MR. So in this example, the minimum regret was 2. And one thing we should note about this solution is that we're evaluating this solution based on the worst case evaluation, or the worst case setting of edge lengths. It actually satisfies the guarantee that for any setting of edge lengths, the cost of the minimum regret solution, which we denote MRS parentheses D, is bounded by the cost of opt for that setting of edge lengths plus the minimum regret. So this regret minimization model is actually a pretty popular model in the operations research community, and a lot of work has been done into studying what problems we can find the minimum regret solution for, or in what problems can we get approximations. So for example, there are certain problems where we do know how to find the minimum regret solution in polynomial time, such as k-center on a tree. However, even for other problems like shortest path and min cut, which we think of in the classical setting as being very easy problems, finding the minimum regret solution is actually NP hard. So to get around this, we can define a notion of approximation algorithms for this model, where we call a solution alg a beta regret approximation if its regret is at most beta times the minimum regret, rather than just the minimum regret. So given this definition, it's actually known that for any problem where the cost is the sum of edge lengths, so this includes shortest path and minimum cut, we can get a 2 regret approximation for problems in P. And there are certain classes of graphs where we can improve the approximation factor from 2 to something like 1 plus epsilon. So in the previous slide, all the problems I discussed results for are problems which the classical version is in P. So natural question is, for example, can we get a beta regret approximation for Steiner tree? So this actually turns out not to be possible, and the idea is that the regret minimization model is more general than the classical model in the sense that if we have all the ranges such that LE equals UE, that is, there's no uncertainty in the problem, then we only have one realization. And if we have one realization, then what does having a beta regret approximation really mean? Well, the optimal Steiner tree for this single realization has regret 0 because it is the optimal solution in the only realization. So then for any finite beta, if we have a beta regret approximation, then it also must have regret 0 because the minimum regret is 0. But that means that for this single realization, it's an optimal Steiner tree, and that means that it's NP hard to find. So getting a beta regret approximation for an NP hard problem is just generally infeasible for any finite beta. So in order to get any reasonable regret guarantee, we need to also have some slack on opt in our definition of approximation. So to come up with a definition of approximation that allows us some slack on opt, let's start by taking the definition of beta regret approximation and noting that any solution that's a beta regret approximation satisfies that the cost of that solution in any realization is at most the cost of the optimal solution plus beta times MR. So a very natural way to extend this and allow some slack on opt is to say that a solution is an alpha beta regret approximation if its cost in any realization of edge lengths is at most alpha times opt plus beta times MR. So we should note here that MR in this definition of alpha beta regret approximation is the same MR in this inequality. That is to say, even though we're allowing some slack on opt in the definition of approximation, MR is still defined as the minimum regret of any solution against an adversary who's playing 1 times opt rather than alpha times opt. So when we look at this guarantee, the intuition you should have for it is effectively, if we have an input where the ranges are very small, this means we have a lot of certainty about the input. And so our approximation definition here parallels the standard notion of classic approximation because this alpha opt term is going to be much larger than this beta MR term. On the other hand, if we have an input with a lot of uncertainty, then beta MR might be much larger than alpha times opt in some realizations. But effectively what this guarantee is saying is even though I'm paying a lot more than opt in these realizations, every solution is going to have some realization it performs poorly in, and I'm not doing that much worse compared to those solutions. So the main result of this talk is that we will give polynomial time constant regret approximation algorithms for TSP and Steiner tree. So one natural idea for how to get such an approximation is to just reduce to the classical problem. And one reason we might hope that this is possible is that for problems in P, this result, which gives a 2 approximation on regrets, actually does exactly this, reduced to the classical problem. So what this algorithm does, which gets a solution with regret at most 2 times MR, is it sets each edge weight to LE plus UE. You can equivalently think of this as setting each edge weight to LE plus UE over 2, because this is just scaling by a constant factor. So the idea is that it's setting each edge weight to the middle value within the range and solving an average case input. So once we set the edge weights to these values, we just solve for the optimal solution, which we can do since the problem is in P. And showing that this has regret at most 2 times MR is pretty simple. In any realization D, we have that alg minus opt can be decomposed into alg minus the cost of MRS in this realization, and the cost of MRS minus the cost of opt in this realization. So the second difference, by definition, is at most MR. So we just need to bound this first difference. To do this, we decompose it as a difference of alg and MRS in the realization L plus U, which is not a valid realization, but we can still think of what this difference is, plus the cost of MRS minus the cost of alg in the realization L plus U minus D. So alg is optimal for L plus U, so of course this first difference is at most 0. And then by definition, MRS has regret at most MR in any realization satisfying the ranges, and L plus U minus D is actually a realization that satisfies the ranges. So MRS can't cost more than MR over any other solution. So we get that this difference is bounded by MR. And so putting it all together, this gives us a true approximation on regrets. So we have this algorithm now, which we know gives us small regret for problems in P. The question is, can we use this algorithm in NP hard problems? Of course, one hiccup is that this algorithm assumes we can solve the problem exactly, but perhaps we can just plug in an approximation result instead. And unfortunately, this ends up not working out. If we use the approximation algorithm as a black box and we run it on a fixed set of weights, namely LE plus UE, it can actually give solutions with very high regrets. So there's a very simple example demonstrating this, which is this example, where you can just think of any problem, say Steiner tree, TSP, even something like shortest path, where effectively we just want to choose an edge that connects these two nodes. And we can see the top edge is obviously going to be the minimum regret solution because its cost is always the optimal cost. And in particular, this means that minimum regret is 0. However, if we use the weights LE plus UE, we can see that the bottom edge is a 2 approximation for this set of weights. So if we try to use this reduction and then apply a black box algorithm, it could buy the bottom edge. However, when the top edge has weight 0, this is a realization of edge weights where opt is 0 and MR is 0, but the bottom edge costs 1. So the bottom edge is not an alpha beta approximation for any finite alpha or beta. So the high level idea here is that while optimal solutions for one set of edge weights can have low regret in all settings of edge weights, the same is not true for approximations. And you might argue that, well, this is a very pathological example. Any approximation algorithm even is going to just trivially buy the top edge over the bottom edge if it's well designed. But we can find similar examples for many variants of this approach, and even for specific approximation algorithms which we use for classical problems. I won't go into the details here due to lack of time. So now that we have some understanding for why we can't just hope to reduce to the classical problem, let's actually introduce the approach which we are going to use in this talk. So this approach is quite simply to solve and round an LP, and the LP has a general form which I've written on this slide. So I'm going to start by taking any polytope P for my classical problem. So for example, I could take the Steiner tree or TSP polytopes here, and I'm going to minimize over X in this polytope, the regret of X, which I'll denote R. And the way that I enforce that R is actually the regret of X is I have this set of constraints, which says that in any realization, the cost of the fractional solution X, which is just the sum over all the edges of the cost of the edge times the fraction of the edge that X is using. This cost should be at most opt plus R, which is to say the regret of the fractional solution should be at most R. One thing to note here is that the only thing that I'm using in writing this LP is that the cost of the problem can be written as some linear function of X. So I can actually apply this to a large variety of problems, not just TSP or Steiner tree. Now, one thing you might note is that there are exponentially many constraints here. So of course, we'll need to design a separation oracle. But not only are there exponentially many constraints, but each of these constraints has a value in it, which is NP hard to compute, which is this optimum value. So we'll address this later in the talk. But that is to say, even just solving this LP is going to be much more challenging than LPs we're used to seeing in other problems. Okay, so solving the LP is actually going to be the harder part of our algorithmic approach. So let's jump ahead a bit and talk about how to round a solution once we've approximately solved the LP. So let's say we start with a solution that's an alpha beta regret approximation. So the key idea here is in rounding the LP, or really just running any algorithm, our goal is to come up with a solution which has low regret when competing against an adversary, quote unquote, who is paying the cost of the optimal solution in each realization. Now the problem is the cost of the optimal solution and the optimal solution itself varies pretty heavily with the settings of edge weights, but we can replace the adversary with one who pays delta times this fractional solution we found. And now this adversary is using a fixed solution throughout all the realizations. And so it'll make it easier to understand how well we're doing against this adversary once we're given a solution. So now our new goal is, rather than find a solution with low regret against opt, we're going to find a solution with low regret against this surrogate adversary who's always paying delta times the cost of the fractional solution. And since the fractional solution has a good regret guarantee, if we have low regret against this adversary, we'll also have a good regret guarantee. So let's say we choose some solution alg, and we want to compute what the regret of alg is against the surrogate adversary who's using delta times the fractional solution we found. So the idea is, for every edge in alg, if delta xc is less than 1, this means that the adversary is paying for less copies of this edge than alg is, and so we maximize the regret by setting de to ue for this edge. And then for every other edge, the adversary is actually paying for more copies of the edge than alg is, so we set the weight to be le. So this means that we can actually identify the realization where our regret against this adversary is maximized, unlike when their adversary is using the optimal solution. So in particular, with a bit of math, we can actually write down the regret of alg against this adversary as the sum of edges in alg of we, where we is this expression. It doesn't matter too much, but just think of it as a weight function that we know explicitly how to write. And then minus some term here that doesn't depend on alg. So the idea is now, if we want to find a solution with low regret against its adversary, this is equivalent to finding a solution that has a low weight using the set of weights we. And so a very natural idea is just to run an approximation algorithm on the graph where we set each edge weight to be we. So in order to analyze how well this approach is going to do, where we find an approximate solution using weights we, we need to understand what does opt for this set of weights look like. And the idea to bound opt is, let's say that delta upper bounds the integrality gap. Then we know that the adversary's cost is an upper bound on opt because the adversary is paying at least the integrality gap times the cost of the fractional solution. So in turn, this means that the minimum regret has at most regret mr against this adversary. And so this expression for the minimum regret solution is at most mr, which means that the weight of the minimum regret solution using weights we is at most this expression here. So this gives us an upper bound on the optimum for the graph with weights we. And now, with a bit of math that I'm omitting here, we can use this to show that if we run a gamma approximation algorithm on this graph, we get a solution with a regret guarantee that looks similar to the regret guarantee of the fractional solution, except we lose the approximation ratio of the algorithm we use, as well as the integrality gap of the polytope we're using. So now that we have a rounding algorithm, we just need to come up with an approximate solution for the LP. So recall that this is the LP I want to approximately solve, where again P here is the TSP polytope. And to approximately solve it, I'll just use standard techniques to reduce to approximately separating it. What do I mean by approximately separating it? Basically, given a solution X, which is in this TSP polytope, as well as R, I want to either find a violated constraint in this set of constraints, which is to say I want to find a realization and an adversarial solution such that the cost of X is at least the adversarial solution's cost plus R. That is, X has regret at least R. And if I can't do this, I want to verify that the fractional solution's cost in every realization is at most twice opt plus R. Since the optimum value for this LP is going to be at most minimum regret, this gives that whatever solution I find by using the ellipsoid method with the separation oracle would be a 2-1 approximation. So how am I going to do this? Well, instead of dealing with these constraints, which contain opt, which as we mentioned earlier is hard to compute, I'm going to use the fact that for TSP, the minimum spanning tree on the graph is within a factor of 2 of the optimal TSP solution. And so what I'll do is I'll replace opt in this LP with 2 times MST, where MSTD denotes the cost of the minimum spanning tree. And now I'm going to exactly solve this LP. And the idea is that this gives us exactly claim number 2, because the cost of the MST lower bounds the cost of opt. And note that this LP contains the original LP. Okay, so now we want to exactly separate this set of constraints. So how are we going to do that? Well, let's rewrite these constraints slightly in order to make it more clear what our plan of attack is going to be. So first, rather than write the set of constraints for all realizations, we can really only care about the realization that maximizes the difference between the fractional solution's cost and the cost of twice the MST. And in addition, we don't really even need to worry about just MSTs. We can consider all spanning trees and then just throw in a maximization over the spanning tree argument. And then, of course, the value of t that maximizes this expression is going to be a minimum spanning tree. Finally, we want to make one more simplification, which is to replace this term, maximization over d, with a term that only depends on one realization. So to do that, let's just assume for simplicity that the fractional solution is actually an integral solution corresponding to the set of edges t prime. So now we can just write the sum as the cost of t prime in this realization. And the idea is that for any fixed spanning tree t, if we want to maximize this expression, to maximize it, every edge that's not in t should have weight ue because it contributes more to the cost of t prime than it does to twice the cost of t. And every other edge should have weight le because it contributes more to the cost of twice t than it does to the cost of t prime. So this gives us that this maximization over all realizations of this difference in costs can be written as some term independent of t minus the weight of t using a certain set of weights. I'm omitting some details here, and don't worry too much about exactly what the weights are. The key thing, though, is that if we substitute this expression in here, we now see that in order to verify that this set of constraints hold, we want to maximize this expression over all t, which is to say we want to minimize this expression over all t, which means we just need to solve the minimum spanning tree problem, where the edges have weight we. And so this gives us the desired exact separation of the set of constraints. Okay, so due to time, I won't be able to go into the full details for Steiner tree, but let me just give you a taste of how that works and what the differences are compared to TSP. So for Steiner tree, we want to solve basically the same LP, except now P is the Steiner tree polytope. So a natural idea is just, well, Steiner tree also has a 2 approximation based on finding a minimum spanning tree. So can we use an MST-based adversary again? So the problem is that this 2 approximation, the spanning tree is a spanning tree on the metric closure. And the metric closure is defined based on what the edge weights are. However, when we choose the edge weights, we choose them based on what the adversary are. So the circular dependence here makes it kind of unclear how one would use an MST-based adversary, and it's even more unclear if this even gives any good results. So since we can't rely on this MST-based approach, we do need to actually just approximately separate the original set of constraints. So let's massage the set of constraints as before, and again, let's replace this max d of difference in costs with some expression only depending on one set of costs. So a simple case is, let's just assume that LE equals 0 for all the edges. Then to maximize this difference in costs, we want to set the weight of every edge in T to LE, which here is 0, and all the other edge weights to UE, since T isn't paying for them. So we get that this max D of the difference in costs, or in other words, the regret of the fractional solution, is the sum of edges not in T of UE XE, which again, we can write as some term independent of t minus the cost of t when we have weights UE XE. So we've done something similar to what we did in TSP, where we've shown that finding some adversary t that maximizes the regret of the fractional solution is equivalent to minimizing the cost of t with respect to some set of weights. So a natural idea now is, since we can't exactly solve for the optimal Steiner tree on the set of weights, to run an approximation algorithm on the set of weights, and hopefully the resulting solution gets, say, fraction 1/2 of the regret of the best adversary t. Unfortunately, if the best adversary, say t star, uses up maybe half the total weight of the graph, then a 2 approximation, we might end up using all the edges, and in turn, the solution will get no regrets. So the standard approximation we know isn't enough, but it turns out that if we run an approximation algorithm with a slightly stronger guarantee, which is that the cost of edges in the algorithm solution that aren't in the cost of the optimal solution is some approximation of the edges in the optimal solution but not the algorithm solution, this actually does suffice to get a solution which gets most of the regret that the best adversary does. So the bulk of our work is to design algorithms that achieve this new notion of approximation, and then we also need to achieve even stronger notions of approximation to modify for the case where LE is not equal to 0. So unfortunately, I won't be able to go into details due to time. So let me just conclude by talking about some open problems. So this rounding and approximately solving framework we introduce is actually much more general. It doesn't just have to be applied to TSP or Steiner tree. So extending it to other problems like survivable network design or set cover seems like an interesting direction. In addition, our algorithm for Steiner tree gets a pretty large approximation ratio, and it also has a very complicated description. So finding either an algorithm with better approximation constants or a simpler description would be a very interesting way to move this line of work. Finally, it would be interesting to see if we can find combinatorial approaches rather than approaches going through rounding and solving LP, since these may provide more intuition. Thank you for watching this talk. I'd be happy to talk more at the Q&A session.